Welcome to this discussion on problem number 394, Decode String. In this problem, we'll explore how to decode a specially formatted string using recursion and stack-based approaches. By the end of this session, you'll have a clear understanding of how to solve this problem efficiently and when to use these techniques. Let's dive in. In this problem, we are given an encoded string S, and our task is to decode it and return the fully decoded version. The encoding follows a specific pattern, k, encoded_string, where k is a positive integer indicating how many times the substring inside the brackets should be repeated. Importantly, this encoding rule allows for multiple levels of nesting, meaning that encoded substrings can themselves contain additional encoded substrings. For input, we're provided with a single string S, and our output should be a single string representing the decoded version of S. Let's look at an example to better understand how this decoding works. Consider the first example, where S is given as 3a, 2bc. To decode this, start by focusing on the individual encoded segments. The substring A is repeated 3 times, which gives us AAA. Similarly, the substring BC is repeated 2 times, resulting in BCBC. When we combine these two decoded parts, we get the final decoded string AAK. In another example, S is given as 3a2c. Here, we encounter a nested encoding. The substring a2c contains another encoded segment, c, which is repeated 2 times to form cc. Appending this to a gives acc, and this entire substring is then repeated 3 times, resulting in a kakakak. This demonstrates how nested brackets are handled step by step. Now, let's look at a slightly more complex example. S equals 2, ABC, 3, CD, EF. First, the substring ABC is repeated 2 times, resulting in ABCAP. Next, the substring CD is repeated 3 times, giving us CD, CD, CD. Finally, we append the remaining portion of the string, EF, to these decoded parts. Combining everything, the full decoded string becomes ABCAP def. This example shows how we process multiple encoded segments and additional characters outside of brackets to construct the final result. When solving this problem, there are a few key points to keep in mind. All encoded substrings follow the format k, encoded_string, where k is always between 1 and 300. Additionally, the constraints specify that the input string S is guaranteed to be valid, so you don't need to handle invalid formats. Be mindful of edge cases, such as nested encodings, where strings like 2, 3, a, 2b require you to handle multiple layers of decoding. Other edge cases include strings without any brackets, such as ABC, strings with very large values of k, like 300, a, and even empty encoded substrings, where something like 3 results in no additional content being added. Understanding these scenarios will help ensure your solution is robust and handles all possible inputs correctly. To tackle this problem, one approach we can consider is a brute force method using recursive parsing. The key intuition here is that the nested k, encoded_string, structure naturally lends itself to recursion. For each substring, we identify the multiplier k and the encoded section inside the brackets, then recursively decode it. Once decoded, we repeat the substring k times and combine it with the surrounding parts of the string. The process involves traversing the string to locate opening and closing brackets, parsing the multiplier right before the brackets, and calling a recursive function to handle the decoding. While this approach works, it has some notable inefficiencies. The time complexity can be as high as n squared, primarily due to the overhead of string slicing during recursion, especially in Python. Additionally, the space complexity is n, because of the function call stack. This can become problematic for deeply nested or very large strings, as the slicing and recursion overhead can significantly impact performance. An optimized approach to address these inefficiencies is to use a stack-based iterative parsing method. Instead of relying on recursion, we use stacks to manage the nested structures iteratively. The intuition here is that we can push each k, encoded_string, onto the stack and build the decoded substrings as we encounter closing brackets. To implement this, we use 2 stacks, one for storing the repeat counts, or k, and another for accumulating the decoded substrings. As we traverse the string, numbers representing multipliers are pushed onto the count stack, while substrings are pushed onto the string stack whenever we encounter an opening bracket. Upon encountering a closing bracket, we pop from both stacks, repeat the substring k times, and append it to the result. This method processes each character in the string exactly once, giving it a time complexity of O(n). The space complexity remains O(n) due to the stacks, but it avoids the slicing overhead of recursion. While stack management requires careful handling, this approach is more efficient and handles nested structures gracefully. Another alternative to consider is using two-pointer parsing. In this method, two pointers are used to identify and parse substrings iteratively, without relying on explicit stack storage. However, this method can be less intuitive to implement and struggles with managing deeply nested structures, making it less practical for this problem. Ultimately, the stack-based iterative parsing approach emerges as the most robust strategy. It balances time efficiency at O(n) and space efficiency at O(n), while being more straightforward to implement compared to the two-pointer method. A key realization here is that stacks allow us to manage nested structures effectively without the performance hit of string slicing in recursion. Recursive parsing, though conceptually simple, was discarded due to its inefficiency for large input sizes. Similarly, the two-pointer method was found to be more error-prone. By avoiding these pitfalls, the stack-based approach provides a reliable and scalable solution for decoding nested strings efficiently, making it the clear choice for this problem. To decode the given string, we start by parsing it step by step. The input string adheres to the pattern k, encoded_string, where k is a positive integer that represents how many times the encoded_ string should be repeated. The encoded_ string itself can either be plain text or another nested encoded string. As we traverse the string, if we encounter a number, we accumulate its digits to determine the multiplier k. When we see an opening bracket, we push the current multiplier and the current partially decoded string onto a stack. At this point, we reset k and the current string to prepare for processing the nested segment. If a closing bracket is encountered, we pop the stack to retrieve the previous multiplier in string context. We then decode the current segment by repeating it k times and append it to the previously stored string. If the character is a letter, we simply append it to the current string since it represents plain text. This systematic parsing ensures that we handle all components of the input string properly, whether they are nested or not. Once we parse the string and manage the nested segments using a stack, our next task is to build the fully decoded string. This happens incrementally as we traverse the input. By the time we finish processing the entire string, the result will be ready. The key insight here is that the problem exhibits a recursive structure. The k, encoded_string, pattern naturally lends itself to recursion, and our use of a stack replicates the behavior of a recursive call stack in an iterative approach. This design is efficient, as it ensures that each character in the input string is processed exactly once, giving us a time complexity of O(n). Furthermore, we handle edge cases like an empty input string by simply returning an empty result. Non-nested strings are treated as plain concatenation, and deeply nested strings are managed effectively by ensuring the stack maintains the correct context at every level of nesting. To implement the solution effectively, we rely on two primary data structures. First, we use a stack to store tuples containing the current multiplier and the partially decoded string up to that point. This allows us to maintain context as we traverse the string and encounter nested segments. The stack is essential for managing the transitions between different levels of nesting. Second, we use a string builder to construct the final decoded string efficiently. By appending partial results as we process the string, we avoid the overhead of repeated string concatenation. Let's consider an example to see how this works in practice. Given the input string 3, A2C, we'll step through the decoding process to understand how these structures interact to produce the final result. We begin decoding the string 3, A2C, by traversing it character by character. First, we encounter the digit 3, so we set the multiplier k to 3. When we see the opening bracket, we push the tuple, 3, onto the stack, representing the current context. Moving on, we encounter the letter A and append it to the current string, resulting in a. Next, we find the digit 2, so we update k to 2. Another, and we push 2 onto the stack, indicating that we're entering another nested segment. At this point, the letter C is appended to the current string, forming C. When we encounter the closing bracket, we pop the stack to retrieve 2, We decode the current segment by repeating C 2 times to get CC, which we append to a, resulting in ACC. Finally, another leads us to pop 3 from the stack. Repeating ACC 3 times gives a cac, which becomes our final decoded string. Throughout this process, the stack ensures that the correct context is maintained, and operations like string multiplication handle the decoding efficiently. The algorithm is both time and space efficient. The time complexity is O(n), where n is the length of the input string. This is because we process each character exactly once during the traversal. For space complexity, we require O(d), where d is the maximum depth of nested brackets in the input. This accounts for the stack's growth as it stores context for each level of nesting. These complexities make the algorithm well-suited for handling strings with varying levels of complexity, from simple cases to deeply nested ones. By leveraging the stack and efficient string operations, we achieve a robust solution that balances clarity and performance. This implementation decodes a given string that follows the pattern of nested encoding. The solution uses a stack-based approach for managing nested structures. The decode string function starts by initializing 3 variables, stack4 handling nested contexts, current_string4 building decoded content, and current_number4 tracking the multiplier. The function iterates through each character in the input string. 1. If the character is a digit, it updates current_number by multiplying the existing value by 10 and adding the new digit. This handles multi-digit numbers. 2. If the character is, it pushes the current state, the current_string and current_number, onto the stack, then resets current_string and current_number for the nested level. 3. If the character is, it pops the top state from the stack, retrieves the previous string and multiplier, and concatenates the decoded string multiplied by the multiplier to the previous string. 4. For regular characters, it appends them to current_string. Finally, the fully decoded string is returned. This approach efficiently handles nested patterns and ensures correctness for all valid inputs. Here, we begin by importing the necessary utility classes and defining our solution class. The method decodeString takes a string s as input, which represents the encoded format. To manage nested decoding, we use 2 stacks, string stack to store the intermediate strings and count stack to store the corresponding repeat counts. We also initialize a string builder called currentString to build the ongoing decoded string, and an integer current number to accumulate digit characters into a full number. Next, we loop through each character in the input string. When we encounter a digit, we update current number by multiplying the previous value by 10 and adding the numeric value of the current digit. This allows us to handle multi-digit numbers. When we reach an opening bracket, it signifies the start of a new encoded segment. At this point, we push current number onto count stack and the current state of current string onto string stack. Then, we reset current number to 0 and current string to an empty string builder to start fresh for the new segment. If we encounter a closing bracket, it indicates the end of an encoded segment. We retrieve the repeat count from count stack and the previous string from string stack. Using these, we repeat the current string the specified number of times and append it to the previous string, effectively decoding this segment. The result is assigned back to current string to continue processing any remaining characters in the input. Finally, once the loop finishes processing every character in the input string, we return the fully constructed current string as a regular string. This represents the completely decoded version of the input. The method efficiently handles nested and sequential encoded segments by leveraging the stack-based approach, ensuring that each segment is decoded in the correct order. The use of separate stacks to manage strings and counts, along with the dynamic construction of strings using String Builder, ensures both clarity and performance. With this, the implementation of the decode string function is complete, providing a robust solution to decode any valid input as described in the problem. To solve this problem, we utilize a stack to help manage nested encodings and construct the result step by step. Starting with the input 3a, 2, bc, we initialize an empty stack, an empty string for the current substring, and set the current number to 0. The first character we encounter is 3, which is a digit, so we update the current number to 3. When we see the opening bracket, it signifies the start of a new encoded segment. At this point, we push the current string and number onto the stack, which allows us to preserve the state of the previous context. The stack now contains an empty string and the number 3. After this, we reset both the current string and number for processing the substring inside the brackets. Next, we process the character a, which is a letter, and append it to our current string, making it a. When we encounter the closing bracket, this signals the end of the current encoded segment. We pop from the stack, retrieving the previous string and number, which are an empty string and 3. Using these, we construct the new current string by repeating the substring a 3 times and appending it to the previous string, resulting in AAA. Moving forward, we process the digit 2 and update the current number to 2. Another opening bracket indicates the start of a new segment, so we push the current string AAA and the number 2 onto the stack, resetting the current string and number again. As we process the letters B and C, we build the current string by concatenating them, making it BC. The next character is the closing bracket, which means we need to decode the current segment. We pop from the stack, retrieving the previous string AAA and the number 2. Using these, we update the current string by repeating BC 2 times and appending it to AAA, resulting in the final string AAPK. With no more characters left in the input, this becomes our output. For this example, the decoded string is AAPK, and we return it as the solution. Now, we examine the input 2, ABC, 3, CD, EF. We initialize the stack, current string, and current number as before. The first character is 2, a digit, so we update the current number to 2. Encountering the opening bracket, we push the current string and number onto the stack, which now holds an empty string and the number 2. After resetting the current string and number, we process each letter inside the brackets, building the string ABC. When we encounter the closing bracket, we pop the stack to retrieve the previous string and number, which are an empty string and 2. Using these, we repeat ABC 2 times and append it to the previous string, resulting in APCAPC. The next character is 3, so we update the current number to 3 and prepare for the next encoded segment. An opening bracket indicates the start of the next segment. We push the current string APCAPC and the number 3 onto the stack, then reset the current string and number. As we process the letters C and D, we build the current string CD. The closing bracket tells us to decode this segment, so we pop the stack to retrieve the previous string APCAPC and the number 3. Repeating CD 3 times and appending it to APCAPC gives us APCAPC. Finally, we process the remaining characters E and F, which are appended directly to the current string, resulting in APCAPC def. This becomes our output, and we return APCAPC def. For the input 10, A, we begin by initializing the stack, current string, and current number. The first characters are 1 and 0, which together form the number 10. We update the current number accordingly. When we encounter the opening bracket, we push the current string and number onto the stack, which now contains an empty string in 10. After resetting the current string and number, we process the character A, appending it to the current string to make it A. The closing bracket signals the end of the encoded segment. We pop the stack to retrieve the previous string, which is empty, and the number 10. Repeating it 10 times and appending it to the previous string results in AAAAAAAAA. This becomes our final decoded string. We return AAAAAAAA as the solution for this input. The time complexity of our solution can be understood as O max_k*n, where n represents the length of the input string, and max_k is the maximum repeat count, or multiplier, in the string. First, the algorithm processes each character in the string exactly once, resulting in a base traversal cost of O, n. Next, when a closing bracket is encountered, the algorithm multiplies the current string by the number preceding the bracket. This multiplication takes O, k, time, where k is the multiplier. While this could theoretically occur for every character in the string, the hierarchical application of multipliers ensures that the total cost remains bounded by max_k*n. Lastly, the stack operations used to store and retrieve pairs of current strings and multipliers involve constant time pushes and pops, contributing an additional O, n, overall. Together, these components make up the time complexity of the solution. By combining the traversal cost of O, n, with the maximum contribution from string multiplications, which is O, max_k*n, we arrive at the final time complexity of O max underscore k asterisk n. Now, turning to the space complexity, the solution requires O m plus n space, where m is the maximum depth of nested brackets, and n is the size of the output string in the worst case. The stack accounts for O m space since it stores pairs of current strings and multipliers for each nested level. Meanwhile, the current string variable, which holds the decoded result as it grows, can require O n space in the worst case when all characters are expanded. Therefore, the total space complexity is the sum of these two components, O m plus n. When comparing this optimized solution with a brute force approach, the differences are significant. A naive method might involve recursively decoding substrings and directly concatenating strings, which leads to redundant operations. This inefficiency could result in a time complexity of O n squared, or worse due to repeated string concatenations. By contrast, the optimized approach leverages a stack to handle nested structures efficiently. Each character is processed once, and string multiplications are performed only when closing brackets are encountered. This makes the solution far more efficient, with a time complexity of O max underscore k asterisk n, and a space complexity of O m plus n. Looking at specific cases, the best case scenario occurs when the input string has no nested brackets, reducing the time complexity to O n. For average cases with moderate nesting, the time complexity remains O max underscore k asterisk n. Finally, in the worst case, with deeply nested structures and large multipliers, the algorithm still maintains its upper bounds of O max underscore k asterisk n for time and O m plus n for space. To mathematically validate the big O analysis, consider the following: each character in the input string is processed exactly once, contributing O n to the time complexity. String multiplications are performed at most once per character, with their cost proportional to the multiplier k. Summing these costs across all characters yields O max underscore k asterisk n. Stack operations, which involve constant time pushes and pops, contribute an additional O n. For space complexity, the stack usage grows with the nesting depth, requiring O m space, while the decoded string size can reach O n in the worst case. Combining these observations, we confirm the overall time complexity is O max underscore k asterisk n, and the space complexity is O m plus n. When solving the decode string problem, there are a few common mistakes to watch out for. One frequent issue is incorrect recursive parsing. If you fail to properly handle nested structures, such as deeply embedded k, encoded underscore string, patterns, you might end up with partial or incorrect results. It's vital to ensure that your recursive calls manage both the multiplier and the encoded content accurately at every level of nesting. Another pitfall is string index management errors. If you're not careful with advancing your pointer after processing a closing bracket, for instance, you could end up in an infinite loop or skip critical parts of the string. Additionally, when you use stacks to decode, forgetting to reset temporary variables like the current multiplier or decoded string after popping from the stack can lead to incorrect outputs. Large input sizes also pose challenges. If the multiplier k is very large, directly constructing the decoded string in memory can cause overflow or memory errors. A smarter approach is to build the output incrementally in smaller chunks or use a generator to reduce memory usage. Finally, don't overlook input validation. Assumptions like balanced brackets or non-negative multipliers can cause runtime errors if the input is invalid, so always account for edge cases in your implementation. Now, let's focus on some key insights for interviews. Decoding problems often rely on recursion due to their naturally nested structure, so it's important to showcase your understanding of recursive patterns. Clearly explain your base and recursive cases to demonstrate a strong grasp of the problem. While recursion is intuitive for these problems, iterative solutions using stacks are often preferred in an interview setting because they eliminate concerns about recursion depth limits. Be prepared to discuss the trade-offs between these approaches. Another critical point is edge case awareness. Interviewers will want to see that you've thought about scenarios like empty strings, deeply nested brackets, or very large multipliers. Finally, don't forget to analyze the time and space complexity of your solution. For instance, a recursive approach might have a time complexity of O n, but require O d space, where d is the maximum depth of recursion. Highlighting these factors can set you apart as a candidate who understands both the implementation and the underlying trade-offs. To expand your practice and deepen your understanding, there are related problems you can explore. For example, LeetCode 394, the decode string problem itself, is a great starting point for mastering nested string decoding. LeetCode 726, number of atoms, involves parsing and decoding chemical formulas, which also uses stack-based parsing techniques. Then there's LeetCode 224, basic calculator, where you evaluate expressions with nested parentheses, and LeetCode 227, which is a variation that focuses on handling operators without parentheses. Beyond these problems, you can try alternative approaches to decoding. For instance, stack-based iterative parsing is a robust solution that avoids recursion depth issues and can be more space-efficient, though it often results in slightly more verbose code. Another option is two-pointer parsing. By using two pointers to parse the string and decode it in place, you can reduce stack usage significantly. However, this method is harder to implement for deeply nested cases, making it less intuitive despite its space efficiency. For scenarios involving large outputs or high multipliers, consider using string builders to construct the result incrementally. This approach can handle large inputs more gracefully by avoiding the memory overhead of directly constructing the full string in memory. While this adds some complexity to your implementation, it's a practical solution for cases where output size could otherwise become unmanageable. By breaking the output into smaller chunks and appending them efficiently, you can create a solution that scales well even for extreme input sizes. This technique highlights the importance of balancing performance optimization with code readability and robustness in advanced problem-solving scenarios. Great job making it to the end. Today, we successfully decoded a nested string format using recursive and stack-based methods. Remember, recursion is invaluable for nested structures, and analyzing multiple approaches is key for optimization. Thanks for watching, and don't forget to like, subscribe, and stay tuned for more coding tutorials. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!